Most people think they know what nothing means. An empty room, a vacuum, space with everything removed. The word feels clean. It feels final. It feels like the one concept that should not need explanation. Physics uses this word constantly. Empty space, vacuum energy, particles appearing from nothing. We place it into sentences as if its meaning were stable, as if everyone agrees on what it refers to. But here's the problem. Every time physics tries to describe nothing precisely, it quietly replaces it with something else. Not because of experimental error, not because we have not measured carefully enough, but because the theories themselves will not allow nothing to exist. Remove all matter, and fields remain. Remove all energy, and fluctuations remain. Remove all structure, and the equations stop working. The failure is not observational, it is conceptual. Physics cannot operate with true absence. Even the emptiest space we can describe is active, structured, and constrained by rules that cannot be turned off. Tonight, we are not asking where the universe came from. We are not asking why anything exists. We are asking something smaller and much more dangerous. What does physics actually mean when it says nothing? And why does that meaning never survive closer inspection? Physics does not begin with intuition. It begins with operational definitions. What can be measured? What can be predicted? What can be tested? And the moment physics tries to define nothing operationally, it quietly stops being nothing at all. Not because of missing data, not because of a failure of instruments, but because of the internal shape of the theories themselves. For most of human history, true emptiness was considered impossible. Aristotle argued that nature would never permit a void. Remove matter, and something else would immediately rush in to replace it. For centuries, this was not philosophy so much as experience. Early attempts to create vacuums failed. Liquids fell. Containers collapsed. Space refilled itself. The idea that nothing could exist seemed not only wrong, but incoherent. That began to change in the 17th century, when experiments finally succeeded in removing air from sealed chambers. The atmosphere, it turned out, had weight. Remove that weight, and something remained behind. At first, this looked like a triumph for nothing. A space with no air, no sound, no resistance. A void at last. But even in these early vacuums, something stubborn refused to disappear. Sound vanished, but light did not. You could still see through empty space. Light crossed it effortlessly. And this single fact immediately raised a problem. Waves, in the ordinary world, require something to travel through. Water waves move through water. Sound moves through air. So what was light moving through? Physics answered by filling the vacuum again. The luminiferous ether. An invisible substance permeating all space, rigid enough to carry light, yet subtle enough to pass through matter. It was a way to preserve the everyday assumption. If there is a wave, there must be a medium. For decades, this seemed sensible. Space wasn't empty after all. It just contained a different kind of thing. Then experiments failed to find the ether. Light did not behave as if it were moving through a medium at all. The ether collapsed. For a brief moment, physics believed it had finally uncovered something like true emptiness, space without substance, a vacuum with nothing inside. That moment did not last, because as physics advanced into the 20th century, new problems appeared that didn't sound like philosophy. They sounded like measurement. Atoms placed in vacuum behaved differently than expected. Their energy levels shifted, spectral lines split, tiny discrepancies appeared in results that should have been identical. These were not large errors. They were small and precise, the kind of smallness that scientists learn to fear, because it often means reality is not doing what the model says it should do. Something inside the vacuum was interacting with matter. Something was exerting influence even when everything else was gone. This wasn't noise. It was structure. The failure was not experimental, it was conceptual. Physics had been asking the wrong question. We tend to picture the universe as particles moving through space, like dust in a room, like planets moving through emptiness. But at the deepest level we know how to describe, the universe is not fundamentally made of particles. It is made of fields. A field is not just a map that tells you forces at different locations. In modern physics, fields are the stuff that exists at every point of space itself. The electromagnetic field, the electron field, quark fields, the Higgs field. Gravity, in general relativity, is not a force sitting inside space. It is part of space-time structure. In this view, particles are not independent objects traveling through nothingness. Particles are localized excitations of fields, ripples in something that is already there. That already changes what empty space can mean. If a field exists everywhere, then removing particles does not remove the field. It removes only the obvious ripples. The medium remains. Not an ether in the old sense, but a set of fields described by equations. Space becomes less like an empty container and more like a physical participant. And quantum mechanics pushes the problem further, because it forbids stillness in the way we usually imagine it. In classical physics, you can have a system that sits at rest with zero kinetic energy and, in some ideal sense, zero activity. In quantum physics, that picture breaks, not because we are clumsy observers, but because the theory does not allow perfect calm. The uncertainty principle prevents a system from having both perfectly defined quantities at once. It is often explained using position and momentum, but the deeper consequence is broader. Quantum systems cannot be pinned to exact values without cost. If you tried to force a field into a perfectly quiet state with precisely zero energy, you would violate the structure of the theory. The lowest energy state of a quantum system is not zero. It is a minimum irreducible residue, a baseline activity that cannot be removed. This is called zero-point energy, and it exists everywhere, even in perfect vacuum. It's tempting to treat this as mere mathematics. But the vacuum is not merely a convenient fiction. The vacuum produces measurable effects. It shifts atomic energy levels. It alters the magnetic properties of particles. It changes how systems behave even when you have removed everything you thought counted as something. One way to say it is that even when a field is in its lowest state, it cannot be perfectly smooth. It must jitter. It must fluctuate. Energy concentrates and disperses, and because energy and matter are interchangeable, those fluctuations can briefly appear as particles. Electron and positron pairs, photon pairs. They appear and vanish within limits set by quantum rules. They are too fleeting to be directly watched like billiard balls, but not too fleeting to matter. The vacuum is not silent, it is active. Crucially, this activity cannot be turned off without breaking the theory that predicts everything else correctly. If the vacuum fluctuates, then it must exert pressure. This is not metaphorical, it is physical. Place two uncharged metal plates extremely close together in a vacuum, and they attract one another. No air, no glue, no hidden mechanism. The force arises from the structure of the vacuum itself. It has been measured repeatedly with extraordinary precision. Empty space pushes back. At this point, the word nothing has already been replaced by something like a field in its lowest energy state. That is not what everyday language means by nothing. But physics is not obligated to preserve everyday language. It is obligated to be internally consistent and consistent with observation. And here is where the concept becomes even more unstable, because the vacuum does not just behave like a restless medium at small scales. It also appears to matter on the largest scales possible. In ordinary matter, pressure is intuitive. Gas in a container pushes outward. Higher temperature, higher pressure. The idea of pressure depends on particles colliding with walls. But vacuum energy behaves differently. Vacuum energy is not a pile of particles bouncing around. It is a property of the vacuum state itself. Because it is tied to space, its behavior under expansion is strange. In the simplest picture, if you have a fixed amount of matter and the universe expands, that matter spreads out and becomes less dense. Matter dilutes. Radiation dilutes even faster. But vacuum energy, in the simplest model, does not dilute in the same way. Create more space, and you do not thin it out. You create more of the vacuum. The density stays the same, and that produces something that feels impossible from an everyday perspective: negative pressure, a tension within space itself. This is the kind of property that, if you met it in any other context, you would treat as a sign that the concept is wrong. But it keeps returning because it does not live in our intuitions. It lives in the equations and in the observations. When astronomers measured the expansion of the universe, they found something deeply unexpected. The expansion is accelerating. Galaxies are not merely drifting apart, they are being pushed apart faster and faster over time. Something is driving this acceleration. And the simplest explanation, within the structure of our current models, is vacuum energy. Not stars, not matter, not radiation. The space between galaxies. Today, roughly 2/3 of the total energy content of the universe appears to be associated with what we call dark energy. And the simplest version of dark energy behaves like vacuum energy. Uniform, persistent, not clumping like matter, not fading like radiation. A property of space itself. If nothing were truly nothing, this would be impossible. And yet here lies one of the most severe failures in modern physics. When physicists calculate how much energy the vacuum should contain using quantum field theory, they get an answer that is catastrophically wrong. Not by a factor of 2, not by a factor of 1,000,000, but by something like 120 orders of magnitude. A mismatch so large it almost stops being a number and becomes a sign that the conceptual foundations are misaligned. Quantum field theory works with astonishing precision in particle physics. General relativity describes gravity and space-time with extraordinary accuracy on cosmic scales. But when these two theories confront the vacuum, they break completely. No known symmetry cancels the energy in the way we would need. No known mechanism explains why the vacuum has the small value it appears to have, rather than the enormous value naive calculation suggests. And no known principle resolves why empty space is both essential to our models and fundamentally inconsistent between them. This is not a gap waiting for better experiments, it is a conceptual failure. Physics does not know how to reconcile its own description of empty space. The vacuum is not a blank background. It is a place where our best frameworks overlap and disagree. And so the word remains: nothing. Used constantly. Defined never, at least not in a way that matches what the word promises in ordinary language. Every attempt to make it precise replaces it with structure, fields, energy, fluctuations, constraints that cannot be removed. Even when physics tries to imagine absolute absence, the equations refuse to allow it. The problem of nothing is not that we have not looked hard enough. It is that our best theories do not permit it to exist at all. Even emptiness obeys laws. Even absence has structure. And that may be one of physics' biggest problems.